Last time we met in class, we have talked about Coulomb's law, and we said that if we have two charges, two positive charges, there will be an electric force between them. That force is a repulsive force. The two charges will repel each other. So we can find the direction of the force by knowing what type of force we have, if it's a repulsive force or an attractive force. So, but if we have one charge, if you have one charge, that charge will create around it a field. That field, we call it an electric field. It's exactly as if you put a perfume. You create around yourself a field that anyone come closer to you will smell that perfume. And how strong is the smell, it depends on the distance between you and that person. Same thing the charge do. The charge create around it an electric field. If any charge come closer to that charge, it will start sensing that electric field, and it might get attracted to it or repelled it, depending on the two types of the charges. So we have around that charge Q an electric field. So assume that I'm a charge. Electric field is a vector quantity. It has a magnitude and direction. Let's concentrate on the direction of the electric field for now. And the magnitude, we'll talk about it in a minute. If I'm a positive charge, and if you put another charge in here, in what direction will that other positive charge move? That direction. So if you have, I'm going to call that a test charge. That thing I'm going to call it test charge. It's going to test for me the direction and the magnitude of the electric field. So if I'm going to put that test charge, and usually when I say test charge, I mean a positive charge. When I put that test charge in here, it's going to move in that direction. It moves in the direction of the electric field. I'm going to put it in here. What direction will that test charge move? In what direction? In that direction. So this is going to be the direction of the electric field from me. From that charge, from me. And if we put that test charge one more time in here, then the direction of the electric field is going to be in that direction. And if you put it in here, the direction of the electric field is going to be in that direction. And if you put it in here, the direction of the electric field is going to be in that direction. Then we can conclude that if you have a positive charge, the direction of the electric field from it will be out of the charge, and it's radial. It goes as radius. So the electric field, the magnitude of the electric field at that point, at a distance 1 meter from me, it's the same magnitude as the magnetic field at that point, the same magnitude at the electric field at that point. So if you draw a circle around me, the magnitude of the electric field along that circle is going to be the same. The magnitude is the same, but the direction is different. Okay, guys? Then we know what will be the direction of the electric field from a positive charge. What happens if you have a negative charge? If I am a negative charge, let's do the experiment again. I'm going to use a test charge, which is always positive in here. And if I'm a negative charge, in what direction will the positive charge, the test charge move in? In what direction? It's going to move in that direction. And if you put it in here, what's going to happen to it? It's going to move in that direction. And if you put it in here, it's going to move in that direction, and so on. So actually, the electric field from a negative charge is inward. It's into the charge. And the magnitude, if you draw a circle around it, the magnitude along that circle is the same. It does not change. So now we can find out the direction of the electric field, and we know that its magnitude is going to be the same along the same circle. Let's calculate the electric field. If you remember the electric force from two charges, if we have a charge Q1 and a charge Q2, the force between them equal to K, Q1, Q2 divided by the distance between them squared. And it has a magnitude, a direction. So simply we can say that Q1 has an effect. It creates around it an electric field. That electric field will attract or repel Q2 depending on the type of the two charges. So actually this is the electric field. Q1 will create an electric field around it, and we can rewrite that equation as the force between charge number 1 and charge number 2. It's Q2 times E, and E is the electric field that's produced by charge number 1. So we can simply say that the electric field is the vector quantity from a charge Q1 equal to K Q1 over R squared. Then someone will say, what's R squared? R squared is the distance that you need to find the electric field at. So now, let's go back to that example that I'm a positive charge, and let's calculate the electric field everywhere. What's the electric field at Amr, right? Amr? At Amr position. Magnitude, only magnitude. What is the electric field from me? It's K, it's K, Coulomb's constant, times Q, divided by that distance square. And in what direction will be that electric field? What is the direction of that electric field? If I'm a positive charge, it's going to be along that direction. Right? Guys? Right? Ala, right back there. You need to find the electric field at Ala location. Magnitude and direction. Simply, it's going to be K, Coulomb's constant, times Q, my charge, the charge on me, divided by the distance between the charge and the point of interest, the point that we need to find the electric field at, which is Ala position, divided by that distance squared, and it's going to be in that direction if I'm a positive charge. Yes. Direction. If it's a positive charge, then the direction of the electric field is out of the charge. That depends on how you want, which coordinate system do you use. If you use a coordinate system, then you write the direction. Then you have to decompose that vector into two components, an x and a y component. Yes. Or if you want to use the polar coordinate system, then it's an angle. Okay, you write the magnitude and the angle that makes with the positive x-axis. Okay? So this is how we calculate the electric field. Simply, the electric field is the force between the two. That's the definition of the electric field. It's the force between the two charges divided by the tested charge, Q. So now if we need to calculate, if I'm going to assume that all of you guys, all of you are positive charges, and we need to find, that's the case, all of you are positive charges, and we need to calculate the electric field at my position, at that point. We need to calculate the electric field from all of you at that point. What to do? So simply I'm going to choose the first charge and calculate the electric field from the first charge. It's going to be K, Q1, divided by that distance square. In what direction? In that direction. Then you have to resolve that electric field, that vector, into two components, x and y component. And write it down as an x and y component. That's one. Then take charge number 2. Calculate the electric field from charge number 2. It's going to be K, Q2, divided by that distance square. And in what direction will be that electric field? It's going to be along that direction. Along that line, along that direction. Then you have to resolve that vector again as an x and y component and write it down. And keep on doing this till you finish the whole 30-something charge that we have. add them together as vectors. And this is how we calculate the total electric field at that position. And that's easy. It's boring. It's a long process if you have many charges. But it's a straightforward process. But now if we have a continuous distribution of charges, let's assume that I have a wire, and on that wire we have put few charges. So it has, that wire has a length of L, and it has on it a charge equal to 10 coulombs. And we need to find the electric field at that point. So what to do?
We divide that wire into small parts.
Okay.
Each part is dx. And then we find the direction of the electric field from this part, and we integrate the whole formula.
Good. I forgot your name.
Karim.
Karim is saying, well, that's not. I'm going to apply the same principle. I'm going to assume that this is my line. And I'm going to divide that line into small parts. Part number 1, that's part number 1, and that's part number 2, and that's part number 3, and so on. And I'm going to calculate the electric field from each part using the same formula. It's K. I'm going to call it dq. K times dq. K times the small charge from part number 1. But I have to divide it into equal parts. So this part, which is part number 1, it has a length of dx, and when I say dx, I mean a small length, and it has a charge dq. That part has a length of dx, and it has also a charge dq. The third one has the same length, same charge, and so on. So from part number 1, the electric field is equal to K times dq times the charge on that part divided by that distance squared. And for part number 2, the electric field equals to K times dq, same charge, divided by the new distance r2 squared. And if you keep doing this and if you add them up, you end up by calculating the electric field. By adding them up, we mean here, since it's a continuous distribution of charges, then that summation, instead of adding them up by summation, that summation should be converted into an integration. And if you solve that integration, you should be able to find the electric field from that whole straight line. Okay guys, example. So let's have an example for this. Sorry. Yes. That's the end of 23. Yes. So I'm going to assume that I have an infinite wire, a wire that's very, very long. And at that point, at some distance here, at point A, we need to find the electric field at that point from that infinite wire. And when we say infinite wire, guys, I do not mean that it does not have a dimension. It may have a dimension, but when I say it's infinite wire, that means that the length of the wire is much, much more than that distance A. So this can be an infinite wire if we calculate the electric field just right here. And the length of the wire is much more than the point that you're trying to find the electric field at. This is the definition of anything that's infinite. So let's find the wire has a length L and it has a charge on it Q. And this is a good time to introduce what we call the charge density. Linear charge density. So I'm going to say the charge per unit length. This is what I mean by linear charge density. The charge per unit length for that wire is equal to Q over L. That's easy. And this is a constant. So if you take 1 centimeter from here, the charge on it, that's lambda, the charge per unit length, the charge for 1 centimeter, for example, or 1 meter. If you took another 1 centimeter in here, the charge on it is going to be lambda. The charge for 1 centimeter on that part, that's lambda. That's what we mean by charge density, linear charge density, or lambda. Someone will say, but what's going to happen if you have a table like this, and you have on that table a charge Q distributed all over the surface of the table? So what will be the charge density in that case? So in that case, we do not call it lambda. Okay, we call it sigma. And in that case, we call that surface charge density. And we call that linear charge density. And sigma in that case equals to Q over A. The charge on that table divided by the area. Assuming that the thickness of the table is very, very small compared to any of the dimension of the table. But if we have an object like this, which is the dimension is almost compared to each other, the length, the width, and the height is almost compared to each other. And if we put some charges on it, and the charge goes everywhere, on the surface, inside the material, the charge goes everywhere. The charge distribution in that case will have another constant that we're going to call it volume charge density. And the volume charge density in that case, I'm going to give it a symbol of rho density, which is equal to, and the volume charge density in that case is going to equal to Q over the volume. So here the units for lambda, can you guess what will be the units for lambda? Units? Coulombs per meter. And here, coulomb per meter squared, and here, coulomb per meter cubed. Those are three important quantities because they actually simplify things for us, and we'll see how. So going back to the problem, we need to find the electric field. We need to find the electric field at that point. So guys, the trick that we said at the beginning that I'm going to divide those into small parts. The length of that part, its length is dx. Right? Guys, right? Alright. How much charge do we have in here? dq. I'm going to call it dq. It has a charge of dq. And that distance, I'm going to call it r. That distance from that point, I'm going to call it x. This is the 0 point. That distance as x. And we call that angle theta. Okay, guys? Now let's find out the electric field from that part only at that point. Direction. Well, direction, that's easy. That's the direction. Magnitude. The electric field from that part, that small part, at that point would equal to K dq. It has a charge of dq divided by r squared. Perfect. Can we give a symbol for that electric field? dE. I'm going to call it dE because it's a small part of the electric field from the whole wire. So I'm going to call it dE. Right? Right? Amir? Amir, are you okay? Okay, good. How can we find the electric field from the whole wire? Huh? That's easy. Electric field from the whole wire is going to equal to the integration of that dE. That's it. Can we get the limits of that integration? Yes, from the beginning of the wire to the end of the wire. From negative infinity, negative infinity to infinity. Excuse me?
How long is the wire?
It doesn't matter. Oh, we'll see. That's a good question here. He said, that infinity bothers me. I need a numerical value to deal with. That infinity, it does not actually make me feel good. I want to change that into a numerical value. I need numbers in there. We'll find out. If that part, guys, is drawn in here at the same distance x, it will create an electric field in what direction? Correct? Right? What is the electric field? The magnitude of that electric field? Same dE. If I choose that to be my coordinate system, would you please resolve dE into two components? That dE, that one, the red one. It will have a component in here that's dE cosine theta, and we'll have another component in here that's dE sine theta. Perfect. How about the blue one? Can we decompose it into two components? That component is going to be dE cosine theta, and that component is going to be dE sine theta. Why am I doing this? Because I want to show you that we have, around that point, we have symmetry. And that symmetry will cancel the x component of the electric field. This component and that component are equal in magnitude, opposite in direction. They will cancel out. So if you choose another part in here and another similar one in here, you will do the same thing again. The x components will always cancel out, and the only surviving component is the component along the y-axis. Are you okay back there? Would you please move closer to me? Okay, guys? No, I didn't mean closer, 10 centimeters close. Can you move in here? Okay, guys? So we have the only surviving component is the component along the y-axis. The x-axis components will cancel out. I'm going to get rid of them. Now I don't need that analysis again. Now if I do the integration from the beginning of the wire to the end of the wire for dE, I will be able to find the electric field, but I have to do the component, the one that's along the y-axis only. The one that's along the y-axis only. dE sine theta, because the cosine theta one will die actually because of the symmetry. It will cancel out because of the symmetry. Okay, good. That's easy. I want to do an integration of dE of sine theta dE. Cannot do. I cannot do that. I can do an integration of sine theta d theta. I can do an integration of x dx, but we cannot do an integration of sine theta dE. I have to convert that dE into d theta. Right? Okay, now let's translate from symbols into equations. dE equals to k dq over r squared sine theta. Still cannot do that integration. I still cannot do that integration. I need to do an integration of sine theta dq. Cannot do it. I cannot do it. Remember what's dq? It's lambda dx. Okay. It's lambda dx. It did not help much. Still, I have to do an integration of sine theta dx. Well, we're almost there. Look at theta. Look at theta. What's tan theta equal to? A over.
Tan theta equal A over.
Yeah. How about sin theta?
A over hypotenuse.
A over R. Right? Good. What's R? What is R? Can we replace R by anything from the graph? Thank you so much. Oh, now we're doing an integration of x dx. It's not an easy integration, but that's okay. Let me finish this, because there is another way to do it. Let me finish this first. K is constant, right? It goes out of the integration. Lambda is also constant. It goes out of the integration. Then we're doing the integration of x dx from minus infinity to infinity. This we can do. That integration you can find it in the integration in any book for integration table if you did not study how to do it. If you did study how to do it, then you should know how to do that. That's easy. But if you don't know it, forget it. If you leave it like this, I'm happy with it. Is there any other way to do it? Is there any other way to do it? Can I go back? Okay, so now that's solved. Look at that integration in any table of integration book. You will find that integration. That's one way to do it. There is another way to do it, which is using what? Using Mabel, yeah. Okay, Ala, if you have a wire that's 10 meters long and it has a charge of 10 coulombs, what is the charge per unit length? Which is one coulomb per meter, right? 10 over 10. Now, what is the charge on 3 meters? The lambda, times length of that part, which is the 3 meters. The charge per unit length times the length. Okay. Okay. Does anyone have a tissue? Oh, thank you. Okay, I'm gonna go back to this. This is one way to do it. There's another way to do it. Again, let me finish. K dq over r square sine theta. على dq that's lambda dx.
share lambda with Q over the entire length of the wire.
Excuse me?
The part of the wire.
على what did you say?
Lambda equals the charge of the entire length of the wire.
No, lambda equals to the charge of unit length of that wire. The charge of 1 meter of that wire, or 1 centimeter, depends on the units that you're using. No, Q, total Q is the charge on the entire wire. Lambda is the charge per unit length.
يعني part of the wire
1 meter. No. Unit length. What is the unit length of that wire? Are you going to use meter or centimeter? So unit length is 1 meter. That's the unit length of that wire. That's lambda. So now if you need to find the charge on 3 meters, you multiply lambda times the length that you need to find the charge on it. 3 meter or 5 or 7, depends on what you want to do. Okay guys, back to here. I want to do that, I want to convert that integration into, instead of having x dx, that lousy integration that we have seen a minute ago, into theta, sine theta d theta or cosine theta d theta. Can we do that? Can you do this? Can you do it? Can you convert that integration into another form of integration that has theta in it, that's over d theta? Replace dx. How would you replace dx? Yes. Sine theta over theta? What's sine theta over theta? No. D theta r? No. That's when we have an arc length. That's the problem in the assignment. It's a straight wire. D theta equal a over x, but d theta does not equal to a over x. Actually, tan theta equal a over x.
D theta equals dA over dx.
Tan theta equal to a over x. No. Who said that? No, this is, guys, do not mix things. There is no d theta here, there is only theta.
dx over r equals cosine theta. Theta is the same anywhere. دكتور ايوه صح. dx over r equals to cosine theta.
Yes. Say that again. I didn't hear you actually. Say it again.
Cosine theta equals dx over r.
And
And then
cosine theta equal x over r and
then there's a dx and the r هنا هنشيل r من تحت نحط cosine theta يبقى r واحدة تحت.
you're almost there, but not the right way to do it. Yes. K. Yes, we know that. Here you go. And that's what we did a minute ago. Perfect. Say that again. R square equal to R equal to
r squared هتبقى equal in terms of triangle.
okay.
دكتور بشير هتبقى a over r.
A over R. Yeah, that's sine theta, right? Sine theta equal over A over R. Perfect. And R equal A over sine theta. Then r squared equal to a squared over sine squared theta. And 1 over sine theta, that's equal to?
1 over sin theta cosine. فهتبقى بقى sin cube theta over.
Well, you're almost there, but we have to do it that way. We have to find a relation. This is the way to do it, yes. You have to find x equal to r something. X over r, that's, what's x over r?
Sin theta. X equal r sin theta.
And that's x equal to r cosine theta. Then integrate that equation.
Differentiate.
Oh, sorry. Sorry. Yes, you're right. Differentiate that integrate. dx equal to
or sin theta. Negative or sin theta.
then you can replace dx by its value. Then you can do the integration.
دكتور طب احنا ليه ما ينفعش نعمل
طب لسه في اه
احنا ممكن نعمل حاجه ثانيه.
Yes.
ودكتور دايما عندك differentiation.
Yes. It's variable. Is r constant or is it variable? Is r constant or is it variable? Yes, it's variable. Why is it variable? Because you look at that r. Look at that r. You see that r, Omar? You see that r? It's not the same r if you take that part in here. It's not the same r. R is not. Oh, you're right. Yes. Can
All depending on the theta.
it does. Is this the book? This is our book. Does anyone have our book? No? A over x, that's tan theta. Okay. Then do that derivative. dx equal to a times the derivative of 1 over tan theta. Tan theta to the negative tan theta sec squared. Then put it in here. You can simplify it. So dx equal to a times sec squared. I don't memorize this. Are you sure? Negative cosec squared. Negative. I don't memorize this. Cosec squared theta. D theta. Equal what? But you're right. He's right. If you remember, let me finish. Guys. If you take sine theta, which is A over R, right? Then if R and theta, they depend on each other. R is still a variable. Same thing. Cosine theta. X over R, which means that X equal to R cosine theta. Those are two variables. They are not constant. R is not constant.
Okay, and I give x in terms of r, substitute the equation.
X in terms of R and substitute, which is R squared equal to cosine squared divided X squared. Then you end up you still have X, which is a variable. This is the only way to do it.
Doctor, when we replace
A over X equal to tan theta, because A is constant in that case. Then X equal to A over tan theta. Dx, let me finish. Dx equal to minus A cosec theta if this derivative is correct. I don't memorize it, but if it's correct, then it's solved. You replace dx by its value.
this sign will be cancelled and there will be sign back. That's it. But it will be 1 over r squared and half theta. So you have two variables.
Yeah, I think the r will be cancelled out by
But by the sign
the sine theta rule. What's the sign?
which which is اللي هي sin theta squared equal 1 over r squared a squared, which we need the 1 over r squared and we'll put the a under the sin theta.
Okay, anyway, guys, this is not the issue. This is not the issue. Now, if we did it by having the integration over dx, guys, and that was a long integration. There is another method to do it is simply by trying to replace that integration over d theta. And it should be a straightforward integration if we get the right relation between r and x. If we, I'm going to redo that again at the end of the class. I'm going to go over it again. It's only the integration.
The answer will be sin theta.
Yeah, makes sense. Sin theta.
The integration would end like after simplification, it will be the integration of sin theta.
Yeah, I know that. Yeah.
And we use the sin.
Yeah, but then if the integration over sin theta, then you have the limits. It's from minus infinity to infinity. Let me finish this. It's from minus infinity to infinity. How can you do an integration from over d theta from minus infinity to infinity? You cannot. But look at that angle theta. Look at that angle theta. If that part is at infinity, what is the angle theta? 0. And remember, we measure the angle theta from the wire to r. So here, we measure from the wire to r. So if this is at infinity, this should be 180. Okay? That's the transformation of the integration from over the length of the x, the length of the wire, to the angle theta. Now we still have that problem. Let me look at my notes. Yes, please.
الكوساك دي زي ما قلنا في الاخر اللي هي الكوساك اللي عملناها وبعد كده هتبقى اللي هي
So dx equal to a minus a cosec squared theta. And cosec squared theta equal to
1 over sin squared.
1 over minus a over 1 over sine squared theta.
Then the other one بقى هنعمل sin theta squared equal 1 over r squared a squared, which is
What do you mean by the other one?
عشان نشيل r squared اللي تحت.
Yeah, the 1 over sine squared theta from here, that's, remember, d theta. Sine theta squared, that's minus a. Sine theta, that's a. That's 1 over a squared
sin theta squared.
r squared. Right? d theta.
ليه حطيت ضغط؟ ايوه عشان انت عملتها differentiation. ضغط لا I mean after اللي هي 1 over sin squared دي خلاص if we put it there it will be like 1 over r squared sin theta squared. انا بقى I'll get out the r اساسا.
Okay. What's sine theta from here? From that? A over r. So 1 over sine squared theta, that's a squared over r squared. So this is that. Then replace. Now we're going to replace dx by its value. We're going to replace dx by its value. It's going to be negative a r squared over a squared d theta. And if you look at this, then it's r squared will cancel out. Then you have a 1 over a sin theta. The 1 over a is constant. A does not change. If you take that part here or here, a is always constant, does not change. So a is constant. It goes out of the integration. You end up having integration of minus sin theta d theta. And the integration of minus sin theta d theta, that's k lambda over a for cosine theta from 0 to 180. That's the other way to do it. But again, that integration is not that important. The important is how can we actually find the electric field from a continuous distribution of charges. Again, the way to do it is we divide that charge into small parts, find the electric field from one of them, and look at the symmetry if we have any symmetry, then do the integration from the entire shape to the end of the shape.
What if you don't have any symmetry?
Then you have to do the integration over the x component and the y component and add them as vector at the end. Okay? Mm-hmm. Well, for this level of electricity and magnetism, this level of the course, I cannot give you something like this. But if 500 level course, you might get something like this, because it has some other way to do the integration. The main problem is going to be in the integration. So you can use some other ways to do it, like green function, something that you did not hear of yet. But I'm going to go over before we go to Gauss's law to the problem and the assignment. In the assignment we have this, a semicircle, a charge, a wire that has a length L, and it has that wire has a length L and has a charge Q, and we need to find the electric field at that point. So what to do? What to do? Ideas? No, you don't answer. You should not answer. You should not answer. Guys, what should we do? Yes, it's in the center. It's in the center. Yes, there is a symmetry.
Y component will cancel out.
Start with? So what am I supposed to do now? If you're in my shoe now, what are you going to do? I'm going to choose a small part that has a length of dx and has a charge on it dq, and the electric field from that part is going to be along that direction. Correct? And that electric field is equal to dE. Right? Right, guys? Right?
Then we'll take another point, exactly the same, but in the opposite side.
Then take another point, exactly the same in the opposite side, and it's going to have an electric field along that side, direction, that point, dE, and it's going to be exactly dE if this is dx and has a charge dq.
The Y components will cancel out.
So if you look at those two parts of the electric field, the Y component will cancel out. If you decompose that, if you resolve that into components, and this into components, the Y components will cancel out. They will be equal in magnitude and opposite in direction. They will cancel out. The only surviving one, if this angle is theta, the only surviving one, that's dE cosine theta. dE cosine theta. Okay, guys? Now, what to do? Omar. So what to do? Now we know what is the electric field. It's going to be along the x-axis, and its component from that part, that's dE cosine theta. We need to find the total electric field, which is the integration all over the top, from the beginning of the wire to the end of the wire. From the beginning of the wire to the end of the wire. Now, let's translate dE equal to
K dq over R squared.
K dq over that distance, which is the radius of the semicircle squared. K dq over r squared. Perfect. What's dq?
K constant,
lambda dx.
Lambda dx. I'm going to replace dq by lambda dx. Remind me, what is dx?
RDQ.
لا.
It's dx. That's the length of that part. It's the arc length. Look at this. That angle here, I'm going to call it d theta. It's a small angle, d theta. What is the arc length? Do you remember in physics 111? Do you remember in physics 111 when we had motion in circular motion? This is R, and we call that angle theta, and this we called it S. The arc length S. Can you relate R to S? S equal to R theta. How did you get that? How did you get that? If you remember, we have assumed at that time that that angle theta is very, very small. So so if this is very small, that angle is almost 90, and this is almost a straight line. This is S, this is R, that's theta. Tan theta equal to S over R, and if that angle is very, very small, then tan of the angle equal to the angle itself. Then S equal to R theta. That's how we got that. We remember it, but this is how we got it. And we call it, this is only valid if theta is very small angle. And this is the case in here. That angle is a very, very small angle. So I can replace dx. I can replace dx by R d theta cosine theta over R squared. Look at that integration. K is constant, right? Goes out of the integration. And lambda. And R. Then the integration is cosine theta d theta. This is the integration of cosine theta d theta, and that's a very easy integration. But we have something that's missing, the limits of that integration. Let's look at the limit of that integration. That was my choice of theta. So if I choose that part here at the beginning of the wire, what is the angle theta? 90. From the beginning of the wire, 90. Till the end of the wire. If this is the angle theta, this is the angle theta. So what is that angle? 270. And then you can solve that problem. That's easy as long as you have symmetry. Okay guys? Okay guys? Okay. Do you have time? 2 minutes. We covered all of this, and those are the two examples. Okay guys, then I'll stop here. On Thursday we're gonna finish Gauss's law.